do it. So you have this rotating thing, and you have a pepper shaker. And it spins with a angular speed of 2 radians per second. It doesn't say which way. And so I'm going to say it's rotating this way at 2 radians per second. And it's slowing down with an angular, I mean, I don't know, that negative there is a little redundant, but it's slowing down. So it's going, it has an angular acceleration this way of 0.8 meter. Okay, that's kind of a mess, but so this has to be radians. This is an angular acceleration. That negative shouldn't be there. So none of that helped make this simple. I will grant you that. And we want to calculate the net force on this thing. The mass is 0.08 kilograms. And we know that this distance is 0.10 meters. Let's choose a coordinate system. So I'm going to have my x-axis this way, my y-axis up, my z point towards the pepper shaker. In order to calculate the net force, so the first thing is we just want the net force on this thing. F net is just equal to the mass times the acceleration. And so we just have to calculate that acceleration, and that's just going to be circular motion. So the acceleration, this is the watermelon equation. All ripe watermelons will rot. Our alpha in this coordinate system that I've drawn, tell me what the components are of that angular acceleration vector. Yeah, the way I have it drawn, I mean, I know everyone did it differently, but the way I have it drawn, this has to be in the negative y direction, according to the right-hand rule. Okay. Anybody have any questions about the right-hand rule on that one? So 0, negative 0.8, 0. The angular velocity, the right-hand rule just has this in the positive y, so 0, 2, 0. And the r vector goes from the center of the circular motion to the object, to the point we care about. Bless you. So that's just 0.1 in the positive z. And now it's just plugging this stuff in. So the acceleration of that pepper shaker is 0, negative 0.8, 0, crossed with 0, 0, positive 0.1, plus 0, 2, 0, crossed with the quantity 0, 2, 0, cross 0, 0, 0.1. This cross product gives you 0.200. And then with this one, you get negative 0.4 in the z. And then this one, we have negative 0.0800. And so this acceleration comes out to be negative 0.08, negative 0.4. And now you can think about whether that makes sense. I mean, it's always a good idea to just sort of sanity check your answers, figure out if there's any way to kind of validate what you've done. Because of the way the angular acceleration is directed, we know that the tangential acceleration is going to be pointing this way. That's the negative x direction. And we know that the centripetal acceleration is toward the center, so in the negative z. And that's what we have. Any questions about that? Okay, so now, oh, that's not the answer to part A yet. We want the net force, but the net force now is just the mass times that acceleration. The mass is 0.08 kilograms. So that is negative 6.4 times 10 to the minus 3, I think. And this is negative 0.032. So 3.2 times 10 to the minus 2. And this is newtons. Any questions about that? What's the magnitude of the normal force? Okay, so now we're going to think about free body diagrams. And this stuff can be a little bit of a pain in 3 dimensions because it's, on paper, it's hard to draw 3 dimensions. So you tend to have to do it kind of plane by plane. But okay, let's draw a free body diagram. And I am going to I'm going to draw it from the side like this. Those are internal details. Don't do that. And what you have going in this view, so anything that's not in this plane that I've drawn, I'm just leaving out. So this is a weight force down of 0.08. So this is 0.7884. Is that right? For the weight. 0.8 times 9.81. 48. 784. Oh, and my decimal is off. And then we have a normal force. And then we also have some friction components. Well, I'm going to call this, so the friction is always going to be acting in the plane of the surface, right? So I'm just going to call this, so if I get my coordinates right, I'm going to call this force of friction, x component. And then these two are in the y component. And we can't see what's happening in the z direction. So I'm going to use Newton's second law just in this plane. That's right, I think. 0.8 times 9.81. Oh, 0.08, you're right. Yes?
Oh, wait, for friction, if you're moving this way, doesn't friction go the other way?
Yeah, I just have it drawn in the direction of the axis. I'm really just putting it in there for sort of completeness. We're not even going to deal with it here. I want to calculate this normal force, which is in the y direction.
Okay.
So really, I'm just going to think about this I'm only going to think about the y component. Okay. And so for forces, we have negative 0.7848 plus n is equal to, we have no acceleration in y. And so that normal force in this case is just equal to the magnitude of the weight. Any questions about that?
Wait, why is it in the y when in the picture above it looked like it was in the z-axis?
The normal force?
Yeah, wouldn't the normal force be going, or is it going straight?
It's going straight out of the surface into the, yeah.
Okay.
You want to try to do it in 3D? I mean, we could try to do it in 3D.
Does it matter? Or will you think?
This is fine.
Okay.
But, different people like to think about these things different ways. It's hard to draw 3D free body diagrams. That's really like part of the problem. But so say we do it at sort of an angle like this. Okay. We have a weight force this way of 0.7848. A normal force this way. And z is going toward the thing. So we have a friction force that I'm going to draw like this. That's an x component and a z component. And those are all the forces. Are you with me? The coordinate system is like this. Okay. And so Newton's second law in 3D now says Fx, 0, Fz, those are the friction forces. Let's call it F friction X and F friction Z. Plus 0 and 0 plus 0 negative 0.7848 is equal to 0.08 times that full acceleration, negative 6.4 times 10 to the minus 3, 0, negative 3.2 times 10 to the minus 2.
Question?
Yeah.
For acceleration, why are you multiplying again by 0.08 if you already did that? Or are you not just using it? Isn't that the whole thing?
Yes, that should be F net. I'm sorry. I was thinking I was looking at the acceleration there. Yeah. Yeah, thank you. And so now, now you do it in 3D. You can calculate the magnitudes of those friction forces. This is negative 6.4 times 10 to the minus 3. N is 0.7848. And FFZ is negative 3.2 times 10 to the minus 2. Any questions about that? And then the last, nope, not the last. What's the magnitude of the friction force? Well, from that three-dimensional calculation, we have that, so that's nice.
That's a good question for me.
Yeah.
You've got the force of the in the XY,
The what?
the force of the friction.
Yeah.
Should that be the force from the acceleration? And then the friction is going in the opposite direction?
Well, once you calculate, I mean, I'm just putting it into Newton's second law, so we know that mass times acceleration is this thing with the negatives. And so force of friction has to be that. I mean, it's just plugging it into Newton's second law. Because, yeah. Okay, so for C now, we know that the magnitude of the friction force is negative 6.4 times 10 to the minus third squared plus negative 3.2 times 10 to the minus 2 squared square root. And that is 0.0326. So that's the magnitude of the friction force. This is in newtons. And then for the coefficient, the minimum coefficient of friction required to keep that in static friction says that 0.0326 is equal to the coefficient times the normal force, so 0.7848 times the coefficient. And so that minimum coefficient of friction is 0.042. And so if the coefficient of friction is smaller than that, this thing will slide. And if the coefficient of friction is bigger than that, it'll stay like fixed to the rotating disc.
Question.
Yeah.
So when you're drawing like the friction, and usually it'd be like negative, does that matter? Because you're going, like if you're like moving this way, you thought.
I mean, I just did it all as
It doesn't matter.
I just did it all as vector components.
Okay.
You know, I didn't try to think about the directions or anything. And then I just plugged those into Newton's second law. And you don't have to really think about it at all, like, you know what the acceleration is. You know, if you add up the forces, it has to be equal to the mass times the acceleration. And so it'll give you those directions. I mean, I think anytime you don't know the direction of something, or if you, I mean, you could think it through in some cases. And then, yeah, sure, you could put in the actual directions. But I'd say most of the time you're better off just calculating it and not thinking about it too much, because sometimes things can surprise you a little. Not in this case, really, but you know, it's surprising how quickly, as complexity increases in the problem, it gets impossible to guess what's going to happen. Anyone else have any questions about this?
How are you? I'm sorry, sir.
What?
How are you? I'm sorry, sir.
They are tomorrow. It's Tuesdays and Thursdays from noon to 2. And then Friday from 11 to 12.
Thanks.
Mm-hmm. Okay, so now number 10. This is pretty similar, but that's okay. Okay, so let's see. It's the same thing, except now instead of the pepper shaker, you have this terrified little kid.
That's why I really asked him what this is about.
Yeah, this stupid kid. What a wiener.
It's their fault for not having a back on them,
For what?
for not having a back on that seat.
That's true. His mom told him not to go to the park that day. There'd be bullies there. Okay, so here's what we're calculating. And let's choose a new coordinate system just to see how it works. So let's go, so if this is the center, let's say that this is the x-axis.
Which is red.
Yeah, y-axis and z-axis up. And it has a radius of 2.2. Oh, it's constant angular velocity. Ooh la la, this is luxurious this time. Okay, so the contact force. Well, so we know we're going to use Newton's second law. We know that because of the Mall of America thing between the parking ramp of kinematics and the mall of kinetics, the skyway is always acceleration. So we know if we're going from kinematics to kinetics, we always have to calculate acceleration. Okay, so that's the first step. So our acceleration is all ripe watermelons will rot. And the angular acceleration is 0. We have to choose an angular velocity direction. It doesn't say. So let's say let's call it this way. That's 5 radians. Oh my God, this kid is going really fast. No wonder he's so upset. Angular velocity. What are the components for this? In the z? Yeah. 0, 0, 5. And then r this time is 2.2 in the positive x. So the acceleration is alpha cross r, and this goes away, plus 0, 0, 5 cross 0, 0, 5 cross 2.2, 0, 0. And that is 0, positive 11, 0. And then these together are negative 55, 0, 0. So this whole thing is 0, negative 55, 0. That does not make sense. 55. Oh, because that should be it should be in the x direction, negative. So this is negative 55, 0, 0. And I caught that by just thinking about going back and saying, okay, there's no tangential acceleration because there's no angular acceleration. And so the acceleration all needs to be centripetal, and centripetal acceleration in this case is in the negative x. Anybody have any questions about that? So if you never make arithmetic mistakes, you never have to sanity check anything, but okay, so there's the acceleration vector. This is in meters per second squared. And now we want to know the contact force applied to the child by the carousel. Okay, so this is, I'm going to do this in 3D, sort of. Okay, so there's the child. And let's think about what forces are acting. There's a weight force down. The child's mass is 20 kilograms, so this is 196.2. And then there's a normal force up. And then there's a friction force that can have X and Z component. I'm not thinking of the right coordinate system. It can have X and Y components. The friction force has to be in the plane of the surface. So I'm going to say that is our F, Y. And that is our F, X. And of those forces, what make up the contact force? Yeah, the friction and the normal force all added up together are the contact force. Okay, so now we'll go to Newton's second law. And it says F, X, nothing for Z, F, Y, plus Z is up, so 0, 0, N. plus 0, what?
Why is Fy in the Z spot?
Because I'm a stupid idiot.
Okay.
Okay. And then the weight force 0, 0, negative 196.2. 1, 2, 3. So that's all the forces. Okay. And then these are equal to the mass times the acceleration, negative 55, 0, 0. And now you can calculate all these things. Fx is equal to 1100. Fy is equal to 0. And n is equal to 196.2. And the contact force is equal to, so these two here are the contact force. So that's equal to 1100, 0, 196.2.
Is there a reason that it's not negative 1100?
No, it should be. Thank you. Okay, so there's the contact force, and we've broken it up into a normal force and a friction force. And what's the normal component? Okay, well, we kind of already did all this stuff. So B says this normal force is 0, 0, 196.2. The magnitude of the friction force is, just the magnitude of, what did we get for that friction force vector? Negative 1100, 0, 0. So that's just 1100. And then what's the minimum coefficient of static friction required so the kid doesn't slip? With the pepper shaker, we got a really low value. Here we're going to get a really high value. So we know that the force of friction, that's equal to 1100, and we're going to set it to the normal force times the coefficient. So that's 196.2 times the coefficient. And so the minimum coefficient of friction is about 5.6. So bye, kid. Coefficients of friction, they can go over 1. It's not like a law that they have to be less than 1. Rubber on concrete can be a little bigger than 1, but I've never heard of one going up to 5. So usually they're less than 1. Any questions about that one? Okay, so now this one we're going to have to use some relative motion. Okay, let's just finish doing these. We'll just do this for today. 11?
I feel like that's probably what we did.
Hmm.
We didn't really-
Yeah. Okay, sketch the system. Net force at the bottom. That is, we have already done that one. Anyone want to see it again? What's the net force at the bottom? It's number 3. Anyone want to see it, or should we skip it?
Yeah, we'll skip.
Okay, we'll do it. So the Ferris wheel is mounted on a train car, which is speeding up at 2.5. I'll do it with things going different directions this time. I think I might have actually done this in class, right? So let's say we have should I do it at a funny angle? No, too hard to draw. Okay, so let's say we have this Ferris wheel and it's mounted to a train car. And the Ferris wheel has a constant angular velocity, I'll say this way. And let's say that the train car is accelerating this way at 2.5 meters per second squared. What's the direction of the velocity vector of this thing, the way I have it drawn? It's always helpful to try to make these kind of connections, I think. So forget about the spinning thing. Just think about the train car for now. So I have its acceleration coming out of the page. It says that the train car is speeding up. So velocity and acceleration have to be in the same direction if it's speeding up. Okay, if it's slowing down, they're in opposite directions. Okay, and the point that we're interested in is down here. The coordinate system, I'm going to go z coming out, x to the right, y up. And we want the net force. So yeah, this is the kinetics of this is pretty simple. All we have to do is come up with the acceleration vector and then just multiply it by the mass. So to calculate the acceleration, there's kind of 2 things we have to consider. So we would use circular motion if our frame of reference is on this train car, okay? If we have a camera mounted to this train car, then we just use circular motion to calculate the acceleration of that red dot. The problem is the train car is accelerating. And so that's a non-inertial coordinate system. Okay, so we're going to have to use relative motion. We have one frame of reference on the train car where this is a simple circular motion. but then we have to account for the acceleration of that frame of reference. Any questions about that? You want any more clarification on that? So the acceleration of person, so let's say the acceleration of the person relative to the ground is equal to the acceleration of the person relative to the train car plus the acceleration of the train car relative to the ground. The acceleration of the train car relative to the ground, as I have it drawn, is just 0, 0, positive 2.5. The acceleration of the person relative to the train car, this is just circular motion, so all ripe watermelons will rot. Alpha is 0. Omega is, that is in the negative z direction, so 0, 0, negative 2, nope, 1.2. And then r, from the center of the circular motion to the red dot, is in the negative y direction, 4.5 meters. So the acceleration of the person relative to the train, this tangential acceleration part goes away. And then we have 0, 0, negative 1.2 crossed with the quantity 0, 0, negative 1.2 cross 0, negative 4.5, 0. So 1.2 times 4.5 is 0.9. So negative 0.90. How can that be? That doesn't make any sense. $5.4. Negative 5.400. And then these give us, in the y direction, a positive value of 6.48. And so this is negative 5.4, 6.480. And then relative motion says the acceleration of the person relative to the ground is equal to negative 5.4, 6.480 plus the acceleration of the train relative to the ground, 0, 0, 2.5. So negative 5.4, 6.48, 2.5.
How did we end up with the 5.4 in the final product?
Yeah.
I thought that was just an intermediate cross product.
You are right. Thank you. Okay, so there we go. And then the net force, that's what it asked for, right? F net is the mass times the acceleration. So 50 times this. So 0, 324, and then 50 times 2.5, 125. Any questions about that? We got a couple more minutes. Yes.
Can you explain, 4B?
Which one?
Exercise 1.
Oh. Um, did I do this one? I think that might be in your notes.
Yeah. It's in the note, but I don't understand.
Oh, you don't understand. Okay, well, yeah, I can. So first you use first draw a free body diagram and use Newton's second law to come up with the acceleration. And then from there, it's just doing the differential equations to go from acceleration to velocity to position. So it's just a differential equations problem. Okay. Okay, let me see what I have time to do about.
Well, I assume it matters in book here.
It does. Okay, so this one thing about this is we're assuming that those books don't have any significant thickness compared to the radius. And so we're assuming they're all at the same location for calculating R. If we had the thicknesses of the books, we could calculate that, but we don't. They're each 1 kilogram. So it has this angular speed. It's going this way at 2.5 radians per second. It's speeding up, so that means that the angular acceleration is also this way. And we're going to calculate the acceleration of those books, and then we're going to draw a free body diagram. So the acceleration is all ripe watermelons will rot. It gives you a coordinate system, which is kind of a crazy one. It needs the y-axis to be coming out this way to meet the requirements of a right-handed coordinate system. And so the angular velocity and angular acceleration are both in the positive y. So alpha is equal to 8.5, 0. Omega is 2.50. That's omega. R is equal to, the radius is 6 meters. You know, the thickness of a book, it tends to be pretty small compared to 6 meters. And that goes from the center of the circle to where the books are, so that's in the negative z direction. So 0, 0, negative 6. And so the acceleration is 0, 8.50 cross 0, 0, negative 6 plus 0, 2.50 crossed with 0, 2.5, 0, cross 0, 0, -6. Okay, and once you have that, so this is the acceleration of each book. Now we want to calculate the force the middle book applies to the top book. So I'm going to do a free body diagram of the top book. And we have a weight force down of 1 kilogram times 9.81. And a force pushing up on it. You can call that N, but that's the force that the middle book is applying to the top book. And so Newton's second law says, what direction is that? Those are both in Z. So we have 0, 0, negative 9.81. Plus 0, 0, N. We also have friction here. So that is, I'll put it in the positive X direction. So let's say this is Fx, and then I guess we also would potentially have a force of friction Y. I'm almost done. So we have F, F, X, F, F, Y, 0. And really both of these together are the force on the top by the middle. And these are equal to the mass times the acceleration that we just calculated. Any questions about that? Okay, that's all. Good class. Good job, everybody.